So when I'm given two sets, the union of any two sets A and B is the collection of all elements in A and all the elements in B. Sometimes this is read out loud, the group A or B. And it's important to note that if an element is in both A and B, we only write it once. So let's let U be our universal set 1, 3, 5, 7, 9, 11, 13. A, B, C, and D are all subsets of U, and they're all proper subsets. So let's go ahead and find the following unions. If I'm looking for A union D, I want all the elements in A and all the elements in D, but I don't want to write any elements twice. So if I look at D, D is 5, but I already have a 5, but what I don't have is a 13. I tried to make that better and I just made it worse. So here's the set A union D. Next, if I want to take B union C, I want all the elements in B. And then I look at C and I say, okay, C has a 3, but I already have a 3. C has a 9, but I already have a 9. What I don't have is an 11. So here's the set B union C. Next, let's take a look at B union D. I want all the elements in B. And then I look at D, and D has a 5, and I don't have a 5, so I'm going to put a 5 in here, and I'm going to write them in numerical order, but it doesn't have to be like that. They'd be equivalent because the order doesn't matter in a set. And then I need a 13. Okay, so B union D is the set of everything in B and everything in D. And because there's no overlap, we get all of the elements. Next, I'm going to take D union the universal set. So I take everything in the universal set. And then everything in D is already in the universal set, so we just get the universal set back out. That's important to note that anything union with the universal set, you're just going to get back out the universal set. Here are the answers. Next thing I want to take is the intersection, okay? So given two sets A and B, the intersection of A and B, written like this, is the set of all elements in both A and B. So the element in the intersection has to be in both A and B. And I believe we taught this last time with a Venn diagram. I want everything in the intersection of A and B. Like, what elements do they share? So let's find some intersections. If I have A intersect C, let's make this a little bigger. Cool. If I have A intersect C, I'm looking for the elements that are in A but are also in C. So let's take a look. Okay, A has a 1, but C does not. A has a 3, and C has a 3. Okay, we'll include that. Next, A has a 5, but C doesn't have a 5. A has a 7, C doesn't have a 7, A has an 11, and C has an 11. So the intersection of A and C is 3, 11. Next, let's take a look at C intersection the universal set. Well, we know that all the elements in C are also in the universal set because these are all elements from the universal set. So the intersection is going to be just C. And that's something to keep, oops, I meant to write an equal sign there. And that's something to keep in mind, that if I take a subset, of the universal set and I intersect it with that universal set, I'm just going to get that subset back itself. Okay, next let's take B intersect D. So B contains a 1, D does not. B contains a 3, D does not. B contains a 7, D does not, and B contains a 9. They have no elements in common. That means that their overlap is the empty set. Next, I'm going to take B intersect U, right? I already told you that any subset intersect with the universal set is just going to give us that subset back itself. If I have two sets with no elements in common, they're called disjoint sets, and their intersection is the null set. Here are the answers. The complement of a set, written x to the c or x bar, are all elements in U that are not in X. This means X union X complement equals U. So what I want, if I'm finding the complement, are all the elements in the universal set that are not in my set. So let's take a look. So if I have A complement, I want all the elements in U that are not in A. So U has a 1, I don't want that. U has a 3, and A has a 3, I don't want that. Nope. A has a 5, and U has a 5, don't want that. A has a 7, A has an 11. So what I want is everything that I didn't underline, and that's going to be 9 and 13. So A complement is 9 and 13. And that's because if I took A union A complement, I would just get the universal set. Okay, let's go ahead and find B complement. So I want everything in our universal set that's not in B, so I don't need a 1. Maybe I should do this in another color, or let's clear this off. That's a better idea. So I don't need a 1 because B has a 1. I don't need a 3 because B has a 3. Oops. It also has a 7 and a 9. So B complement's going to be 5, 11, 13. All right, let's go ahead and take a look at C complement. We're getting lots of compliments today. Ha ha ha. Okay, so C complement, well, U has a 3. So C has a 3, so I don't want a 3. C has a 9, so I don't want a 9. And C has an 11, so I don't want an 11. So C complement is 1, 5, 7, 13. That's going to give me C complement. Okay. Next I'm going to find D complement. D is going to be everything but 5 and 13. Next, U complement. The complement of the universal set, well, because the universal set already contains everything, that's going to be the empty set. Here are the answers. Next, let's talk about relative complements or difference of two sets, okay? So if I want to find the difference of two sets, okay, this is x/y is all the elements in X that are not in Y, okay? All the elements in X that are not in Y. We write this as long as X is an element of that this set, the difference of X and Y, is all X in our universal set such that, that's what those double dots mean, by the way, such that X is an element of X, but X isn't in Y. You could also write this X intersect Y complement. So for A/B, I want all the elements in A that are not in B. So what's that going to be? Well, 1 is an A and not in B. 2 is an A and not in B. 3 is in B, so I don't want that. All right. 5 is in B, so I don't want that. 6 is in B, so I don't want that. I then want 7 and 8. So this is all the elements in A that are not in B. We can also find B, the difference of B and A. So that'd be all the elements in B that are not an A. So 3 is an A, 4 is not an A, 5 is an A, and 6 is an A. So it's just going to be the set of one element, which is 4. And here are the answers to that. The symmetric difference of two sets, X and Y, is the set of elements that are in one set or the other, but not both, okay? This is written formally as X, symmetric difference of Y, is X union Y, the difference of X union Y and X intersect Y. So that means all elements in the union that are not in the intersection, right? If they're in the intersection, they'd be in both, and we want not in both. So let's take a look at A and find the symmetric difference of A and B. So I want all the elements in A. I want all the elements that are in A or B, but not both. So I'm like deleting the intersection. So what do these elements have in common? Well, A has a 3 and B has a 3. A has a 5 and B has a 5. And A has a 6 and B has a 6. So the symmetric difference would be all the elements in A that are not in B, and then all the elements in B that are not in A. So I'd get the set 1, 2, 4, 7, 8. Let's do another example. So I want to find this symmetric difference between S and T. So S is A, B, D, F, G, H, I. And T is all the vowels. So if I want to find the symmetric difference, I have to take all the elements in A that are not in B and all the elements in B that are not in A and union them together. So S has an A and T has an A. B, D, F, G, H, those are not repeated in T, but I is in T, so we can cross that out. So I'm going to have the set B, D, F, that's 1 comma, G, H, E, O, U. And I know those aren't in alphabetical order. But this would be the symmetric difference of these two sets. Here are our answers. But these are in alphabetical order. So one thing I want to say is that two sets are said to be a disjoint if their intersection is the empty set. So here I have X is 1, 2, 3 and Y is 4, 5, 6. These have nothing in common, so their intersection is going to be the empty set. A collection of sets is said to be pairwise disjoint if the intersection of any pair of sets is the empty set. So for example, if I have the set 1, 2, 3, 4, 5, 6, and 7, 8, I can take the intersection of x1 and x2 and get the empty set. I can take x2 intersect x3 and get the empty set, and I can take x1 intersect x3 and I'll still get the empty set, right? So these would be pairwise disjoint. The following sets of 1, 2, 2, 3, and 4, 5 is not pairwise disjoint, and that's because, yes, x1 intersect x3 is the empty set, and x2 intersect x3 is the empty set, but, okay, x1 intersect x2, which we'd have to take, is the element 2, right? So this is not pairwise disjoint. Cardinality of sets, what this is telling us is kind of like the size of a set. So if A is a finite set, we define the cardinality of A to be the number of elements in A, and we write this bars A. So if I want to find the cardinality of A here, A has 1, 2, 3, 4, 5, 6, 7 elements. If I want to find the cardinality of B, it has 1, 2, 3, 4 elements, right? If I defined a set C to be letters in the alphabet, okay, the size of C would be 26. So you can have the set listed or you can have it described and still be able to find its cardinality. So here's the section 1.4 homework. It's on pages 46 to 48. I gave you more problems in this section because I want to make sure we have set theory down. Also, I found this section kind of fun. When you guys submit the homework, I will be posting homework keys so everyone can check their work